All right. Now, I guess we are returning back to our regularly scheduled program, as they say. Ilias is found at University of Wisconsin-Madison. He is an expert on robust mean estimation and everything to do with high-dimensional robust estimation. He's won a number of awards, including the Career, Sloan, also the ACM Grace Hopper Award, and we're really excited to have him.
Welcome, everyone. Thanks for the brave souls that stayed until the end. So I apologize in advance. I'm a little bit under the weather, given the travel issues. So this work is intended to be an overview of recent algorithmic work on learning multi-index models. So these are sort of a family of functions that provide a useful framework to study various questions in machine learning, both supervised and unsupervised. And intuitively, they capture the assumption that's common in many situations, that data has low-dimensional structure. This low-dimensional structure is hidden, and we're trying to find it in some sense. So as such, they are a useful lens for studying a variety of ML models. For example, they're a toy model for neural networks. So here's a definition. So a function f in d dimensions, y is the label set. For most of the theorems of this talk, y is going to be a discrete set. Towards the very end, I'm going to say a little bit about real value functions. So a function f is called a multi-index model with parameter k if there exists a subspace of dimension at most k such that the value of the function on any point depends only on the projection of the point on this unknown k-dimensional subspace. All right? So k, the dimension of the hidden subspace, is meant to be a quantity that's much less than the dimension d. Otherwise, it's kind of, in most cases, it's meaningful. It's meaningless. So if k is equal to d, you can represent any function in this form. It's not quite the case, because if the combining function g is known, you could have k larger than d. For example, if you take a linear combination of ReLUs, you can have more ReLUs than the dimension of the space. In any case, so that's the family of functions. Here are some examples. The most basic example that everyone should know, and it should come to your head first when we're talking about multi-index models, is a linear classifier, okay, or linear threshold function, or a half space. So this is the most basic class of functions in learning theory since the 50s. Like, we had algorithms for learning this class of functions before computer science existed as a field. And what is the algorithm to learn half spaces, the practical algorithm? How is it called? It's called perceptron, right? All right. Now, generalizing this, we get intersections of half spaces. And another generalization is a multi-class linear classifier, which is going to be actually, I'm going to talk about a lot about it, but here is a definition. In terms of real value functions, you can take just a single neuron, so some activation sigma applied to a linear form of w dot x. So this is called a single index model, or a generalized linear model, depending on whether sigma is known or unknown. One hidden layer, so a linear combination of single neurons, is also a multi-index model where k, the dimension of the hidden subspace, is the number of terms in the sum. And under some reasonable assumptions, even a bounded depth neural network can be expressed as a multi-index model. So this is not always the case. Okay, so what you need for that, a sufficient condition, is that this first matrix W1 has rank at most k. Okay, so if it is the case, then this is a multi-index model with parameter k. Okay, now in terms of what we want to do, we want to learn those models. So here is a definition of learning. So I'm interested in pack learning. My loss is going to be the 0-1 loss. So this is what I want to achieve. Okay, find a hypothesis that has small 0-1 misclassification error. I'm not assuming realizability, so the labels that I'm observing are not necessarily from the model in the class. So there is some minimum loss you can achieve, which we call it opt. And we want an algorithm that gives us something that's competitive with opt as good as possible. And again, the goal is to just do pack learning, so find the hypothesis that gives you small loss as opposed to identifying the parameters, the hidden subspace. And these are related but not equivalent. Now, big assumption for the talk is that the distribution on X, so the margin on X, is going to be Gaussian. Now, I could spend about like 15 minutes motivating this, but I'm not going to do it. So I'm going to say that the reason we make this assumption is because we kind of need it, or at least for the general settings that we're looking at. For example, for the people who are in kind of close to learning theory, intersection of two half spaces. If, in the distribution-free setting, we know nothing. Even a linear combination of values. In the distribution-free setting, we know nothing. So really some distributional assumption is needed to have efficient algorithms, as far as we know. In some cases, with label noise is actually necessary. So we're going to assume Gaussian from now on, which is kind of a standard assumption in this field. Now, the prior work in this area is basically extensive. Okay? The punchline is that the case of k equals 1, so if we're trying to learn single index model, is fairly well understood. Not fully understood, but fairly well understood. So there's work for 50 years. The perceptron is an algorithm for such a model. So both in the case that the labels are actually clean, and when the labels have some kind of noise, either random noise or adversarial noise, there are optimization-based algorithms to learn single index models. Okay, so basically, more or less, these are first-order methods, but not fully. When the activation is unknown, you need to do something non-parametric as well. These are actually practical algorithms. Okay, in most cases, they do pretty well. They're not going to be SGD on the standard loss. This fails, probably fails. Okay, so if this is what you want to do, then it just doesn't work. Now, an important thing to have in mind is that even for this toy problem of learning a single index model, there are computational limitations. Okay, in particular, if the link function, this sigma in the previous slide, so this sigma, okay, is arbitrary, the problem is not solvable. So you need to assume something about sigma, and this is even an information theoretic requirement. You need assumptions on the link function, you need assumptions on the distribution, and you need assumptions on the error guarantee. Okay? So some combination of such assumptions is needed to be able to guarantee computational tractability. I'm not going to go into all the prior sort of results on computational hardness, but we're going to see some of them in the next maybe 5-10 minutes. All right, so single index models, more or less understood. Now, multi-index models. Again, there's a lot of work, both in statistics and ML theory. So the statistical work usually cares about rates as opposed to computation. The works in ML theory actually get polynomial time algorithms for many interesting cases. So what's the issue with all of these algorithmic results? One issue is that they work only for very special cases. And the other is that they require clean data. A combination of the two appears in all of those prior works. So ideally, what we would like is to have a general method that is noise tolerant and qualitatively characterizes the complexity of learning. Now, this qualitatively is going to become quantitative soon. All right? And it turns out that the underlying algorithmic ideas in prior works did not seem to suffice to achieve this goal. This has been one of the motivations of this line of work, to make progress on these goals. So the punchline question is this one. So can we develop general methods that are noise tolerant and qualitatively characterize efficient learnability? And the result I'm going to focus on mostly is this one. John works with my students, Yannis Iakovidis, Nikos Zarifis, and my collaborator, Daniel Kane. So this is for discrete valued multi-index models. There's a follow-up for real valued, which I'm going to mention towards the very end. So the main contribution here is a new algorithm that basically, okay, it's tolerant to label noise, both random and adversarial in certain ways. And its computational complexity is qualitatively the best possible as a function of the dimension, not as a function of the other parameters like epsilon, the accuracy, and k, the dimension of the hidden subspace. So basically what this gives us, all of this is under the Gaussian distribution. So if an algorithm with fixed polynomial dependence on the dimension is possible, this gets that, and it gets it with the right exponent. Otherwise, it's not possible. So there is a matching computational lower bound for a restricted model of computation that's called statistical query model. If you don't like this model, you like low-degree polynomials, The same lower bound holds for that model, and also for sum of squares, it also follows. So now its applications, we get better algorithms for the following problems. So one of them is multi-class linear classification. I mentioned that in the beginning. Intersection of half spaces and constant depth ReLU networks. Okay, so this is the advertising of the results. So are there any questions so far? Yes?
What do you mean by you can apply it to constant depth ReLU networks? Like, what does that mean?
What it says, it means that this is an algorithm for a class of functions, okay? This class of functions contains constant depth neural ReLU networks, which means that we update, as a corollary of this general algorithm, we get an algorithm for learning constant depth ReLU network complexity, which is state of the art. Okay, I'm going to have theorem statements later. Okay, all right. So now the technical part of the talk is going to be fairly limited given the time constraints. It's going to be for this basic problem. So multi-class linear classification. So it's enough to illustrate the algorithmic approach. So even for this simpler model. And it turns out that if we take this very general algorithm and we just specialize it for this basic class of functions, it gives us state-of-the-art results, which actually was very surprising to me. And in fact, things happened in the opposite way. We were working on this problem. We got this algorithm for this problem. And then we realized that the algorithm is much more general. It extends to all multi-index models. All right, so let me just define again the class of multi-class linear classifiers. So it's a generalization of half spaces. So this is the definition. So we have functions in d dimensions. You have k different affine forms. You have weight vectors wi, thresholds ti, and the label of point x is a number between 1 and k, and it is then the index of the linear form that is the arc max. Okay, and if we have ties, you can pick the smallest index. It doesn't really matter. So that is the definition of the model, and it's kind of a textbook problem in machine learning, learning linear multi-class linear classifiers. If you have only 2 linear forms, then basically it's like having only 1 linear form, and it's a half space. All right. Now, and of course, this is a very special case of a multi-index model where the hidden subspace is defined by these wi's, and it is basically k-dimensional. So here is an example of a multi-class linear classifier for 4 labels, where all the thresholds are 0, and these are like the normal vectors define these 4 regions. So the colors are basically the sort of half common label. Okay, this is how you partition the space. All right, so what do we know about this problem? So the first thing is information theoretically, we know everything. Okay, standard tools tell us that d times k over epsilon square samples are enough. You can use the ARM and get whatever you want. Computationally, the situation is much more subtle. In particular, if there is no noise, if the labels are actually consistent with the function in the class, the problem is easy. It is just linear programming. Okay? However, if you add even a little bit of noise to the labels, you cannot just do LP. The problem becomes more difficult. And computationally, we understand this problem very well for the case of two labels. For half spaces, this problem is studied to death, and it's more or less fully understood. Okay? On the other hand, essentially nothing is known algorithmically for more than 2 labels. When the dimension k, the number of linear functions, is more than 2, and this is what we're going to explore. Okay? Yes?
Is there any quick intuitive way to say what the algorithms are for the noisy case? Are they iterated LP or?
I mean, there are different cases. So when when the noise is random, then it is kind of a robust version of LP. But it's not easy to describe. It's not easy to describe. And when the noise is adversarial, then you need to make strong distributional assumptions. And for that, the algorithms again are not trivial. All right. So I just want to give you 2 hardened results before I give you an algorithm. just to give you a sense, because like someone could say, okay, for 2 labels the problem is solvable. What's the difference between 2 labels and 3 labels, right? Probably nothing. Turns out this intuition is wrong. So here's like theorem number 1. In the distribution-free setting, okay, just pointing out that in the distribution-free setting for 2 labels and random noise, the problem is solvable in polynomial time, okay, by previous results. But if you have 3 labels, this is not possible. Okay, so you cannot solve the problem in polynomial time in the distribution-free setting for 3 or more labels. Okay, there is a qualitative complexity separation between the binary case and the ternary case. I'm not going to go into the proof of this, of course, but the point is that there is something different between 2 labels and 3 labels. And even for the case that the data is Gaussian, okay, again, and random noise, again, you cannot solve the problem as well as you would like. So, as we said, the sample complexity of the problem without computational considerations is d times k. And what the theorem is saying is that if you actually want to get the optimal error, which is opt plus epsilon, then you need to spend complexity d to the k. Okay, so yeah, this is under the Gaussian distribution, which is what we're working on. Okay, so as a result, so even if we want to get sort of something better than d to the k, which is really a terrible complexity if k scales, then we need to relax the error guarantee. Okay, we cannot get opt. We need to get something weaker, and this is the first sort of algorithmic result that is basically the special case of this general algorithm that I mentioned at the beginning. So for this agnostic model, we can get a sample complexity which is linear in the dimension, some exponential dependence in k and epsilon, and sample polynomial time. And the final error guarantee is going to be a constant times the best possible. So this big O is a universal constant that doesn't depend on any parameters of the problem. Okay, so it's like 10. Okay, and this exponential dependence in epsilon and k, of course, it's not ideal, but at least we separate d and the dependence on epsilon and k. And if the noise was random, we can get something a little bit better. The overall complexity would be 1 over epsilon to the k. So we still have to pay the k in the exponent, but at least the dependence on both d and 1 over epsilon is pretty good. Any questions so far? So that's the first theorem, and I'm going to spend maybe the next 10 minutes explaining how the algorithm works. So does this parse? I mean, I know people who are in this area, and it's I'm confident, but in general, does the statement parse? So the goal is to get a constant factor approximation and to do this in fixed polynomial time, fixed as a function of the dimension. All right. So, okay, how would you solve this problem? What's a natural way to solve this problem? Oh, there are many heuristics of that form, but unfortunately, none of them works. Okay, so what's that?
Why tend to do 1 versus all?
I mean,
you can solve the linear separator itself, and why can't you reduce to learning k-square linear separator?
Right, we want a constant factor approximation, and if you do that, you would get much worse dependencies. Yeah, you could get something, but this wouldn't be a constant factor. Okay, maybe you could get Yeah, sure. If but if k is constant, then d to the k is also poly d, right? So I agree. All right. So let's. So one natural way to solve all of those problems is using moments. Okay, low degree moments of some type. And the standard approach that people have used for these types of questions is use moments over the entire space. Okay, like these are like moments of x, and you have to take into condition on the values of y on the level sets. It turns out that this is not enough, but here is a lemma that motivates what we do. So this is a structural result. So what does it say? It says that so the function f star is a target function. It's a multi-class linear classifier. So if this function is not very close to being constant, okay, so one of the k labels is is this close, then there exists one label, okay, between 1 and k. There exists a label I, such that if you take the corresponding first moment, so the expectation of x on the points where the label is I, so you take k different level sets, then this one of those k different moments is going to be non-trivially correlated with the defining subspace. So W star is the hidden subspace that defines the multi-index model. That's what we're kind of looking for. So suppose we have this structural result, and we do have it. It's true. So how would you solve the problem? So this gives us a starting point, right? So it's telling us, okay, I'm gonna take all of these vectors. You have k of them, and one of them is going to be non-trivially correlated with the hidden subspace. But unfortunately, the correlation is very tiny, so you cannot just use that one direction that you get out of those, but it is enough for some kind of initialization. So the idea is to start from this weak approximation and iteratively improve it, okay? And for such a process, for such an iterative improvement process to work, what we need is that in every iteration, we can find vectors that are correlated with a hidden subspace, and they're new. And what does it mean that they're new? It means that they are orthogonal to the approximation you have so far. So we start from, let's say, one vector that is a weak approximation, and we're going to want to find a vector that is orthogonal to that, a new vector, and correlates with the hidden subspace. So let me give you an illustration of the algorithm.
With the subspace exactly, like the angle?
Or in a product. Like you can say that there is a vector in the subspace that has, not good correlation. Correlation just in a product. All right, so let's say that this is the unknown function, okay, a multi-class linear classifier. So what we want to do is that we don't have the picture, of course, we just have data. So the high-level goal is to partition the domain into many small pieces. And we're going to do this adaptively using the data points. And after we construct this partition of the domain, we're going to output a piecewise constant function defined by the partition. So in each region defined by the partition, the hypothesis is going to be constant. All right, so we do this iteratively, and sort of the partition is refined over a sequence of iterations. So let's say that somehow in the first iteration we calculate this direction, okay? And we said this is a good direction that correlates non-trivially with the hidden subspace. What we do is we partition the space into slabs, into these regions, okay? And yeah.
The hidden subspace is just like plain already, so, or?
I mean, this is not a very good picture, like, I agree, but yeah, but, the second direction is going to be, yeah. There are various issues, okay, with this picture. One of them is that these slabs are of the same dimension as the dimension of the space, while in reality, these are kind of cylinders in a much lower dimensional subspace, so they are infinite in most directions that you do not constrain. But that's what I can do with the two-dimensional picture. All right, so let's say we start with this direction that the initial lemma gives us. We partition the space somehow, okay, into slabs, and then we kind of try to check. Okay, maybe in those slabs, piecewise constant approximation, is it good or not? Does it look good? If you take this slab, can you approximate the function well by a constant? No, right? So you keep going. So you find a second direction, you refine your space more, and you keep doing this until a piecewise constant in each one of those small rectangles that are actually not rectangles, they're kind of cylinders, is good enough. So basically the questions to answer are like, what are these vectors? How do we calculate them? We know how to calculate the first one. Okay, it's going to be one of those conditional first-order moments. How do we calculate the other ones? But after we answer these questions, more or less, the algorithm is complete. So I'm not going to have enough time to give you an analysis, but let me give you the pseudocode. So this is the general algorithm, and this is the subroutine that in every iteration adds new vectors. So let me sort of give you some notation. So in every iteration, let's say in iteration t, the algorithm keeps a set of unit vectors, and this set of unit vectors is L sub t, okay? And the approximating subspace in this iteration is the span of L sub t, okay? And this is what we denote by Vt, okay? So moreover, this set L sub t of unit vectors also defines the partition of the space into cylinders, okay? We just do some kind of fine approximation of the space with respect to the projection on x in these directions. Now, this set L sub t increases in each iteration. We add more and more vectors to it. And as a consequence, we're hoping that this is going to give us a better approximation to the hidden subspace W star. So the routine that goes from L sub t to L sub t plus 1, so how do we add new vectors, is this routine here. The claim is that the set of vectors that we add in the tth iteration, this is, how do we call it here, E sub t, it contains a vector with non-trivial correlation to the part of the hidden subspace that is orthogonal to Vt, which is the previous approximation, okay? And this means that it contains a new direction that has good correlation, and it's also orthogonal to the previous directions, okay? So that is kind of the algorithm. I'm not going to say more about the analysis, since this is a fairly short talk, but if there are questions, I'm happy to answer them.
1K plus 2, does this collapse to a known algorithm?
No, it does not. It does not. Because it doesn't. Okay, so it's not localization based, etc. So it's a different algorithm. No, this is for a diagnostic model. Yes. So, I mean, the algorithm, okay, so one thing I want to say, okay, thank you for reminding me. So, in the adversarial label noise model, the approximation to W star that we construct is not necessarily going to be k-dimensional. We're going to have more dimensions, okay? And this is why we get this ridiculous exponential dependence on epsilon and k. If you had random classification noise, you can guarantee that the approximating subspace is actually going to be at most k-dimensional, and this is why you get a better complexity. All right, so that's, if there are no questions, I'm going to move to some statements. Yeah?
Okay, so this, I guess the key thing is like this matrix is supposed to, like, is there, I guess it's saying that for every sector you're like picking, you're trying to find like repeat the first step condition of that sector.
Exactly. So there are some slides that I have removed from the talk because it's like a 35-minute talk. If the slides were there, it would make sense why we're using SVD on this matrix to actually, so basically in principle, if you don't care about the precise dependence on epsilon and k, and you can live with the power tower, you can add all of those vectors, okay? But this is going to blow up really bad, and this, finding the largest eigenvalues of this matrix here is a way to reduce the size of the number of directions that you use, okay?
Conditioning not, like why is conditioning not change the?
So if you condition in this way, the distribution remains standard Gaussian on the corresponding region, and so the lemma that I had in the very beginning actually applies in each one of those regions S, okay? So if you're interested in more details, I'm happy to discuss this offline. So all right, so let me move on because I can see the time. I've been speaking for 28 minutes. All right, so what is the statement for general multi-index models, okay? So this was a very basic case where we just use conditional first moments over various subspaces. So, okay, so there is a sort of general definition that's going to take me at least 5 minutes to go through, but here's the idea. So if you have a multi-index model, we call it well-behaved if it satisfies the following condition. If you take any subspace V, this is not necessarily the hidden subspace, and we don't restrict the dimension of V. Either this subspace is a good enough approximation, which means that you can use it to learn the function, and this is kind of the first condition, or by computing moments of x conditioned on the value of y and the projection on this subspace, we can learn some previously undiscovered direction in W, okay? So now, this seems like a weird condition, right? But it turns out to characterize the complexity of the problem. And for people who have seen prior work on single index models, in particular something called the generative exponent. So this is a robust generalization of the generative exponent to multi-index models when you want to do pack learning with label noise. All right, so the arguments that I didn't have time to present earlier actually tell you that multi-class linear classifiers are well behaved, and the parameter m in this definition, which is the degree of the moments you need to use in the subspaces, is 1, okay? So okay, now other examples. Okay, so the theorem, what's the theorem? So the theorem is like take any class of multi-index models, okay? And if m star is the smallest positive integer, says that any function in the class is m star well behaved, according to this definition, then you can learn with complexity d to the m times some function of epsilon and k. And in fact, d to the m or d to the m star, this should be m star here, d to the m star is inherent. That any statistical query algorithm for the class C requires this complexity. So as a function of the dimension, this parameter, the smallest integer such that every function in the class is well behaved, actually characterizes the complexity of learning. And again, this exponential dependence in epsilon is not going to be there if we're looking at random noise. Now, so this is the main result, okay? So now, what other applications can we get beyond the? Oh yeah.
Just this definition on the previous slide. Does that assume a known or fixed G, or is
no? So you're saying how is this possible, right?
Yeah.
So because there's another hidden assumption that the class of functions you're trying to learn has some additional regularity. So in particular, like all of these algorithms. So thank you for asking this. All of these algorithms, they are trying to reduce the problem down to ideally k dimensions. But after you have reduced the problem down to k dimensions, it's not necessarily solvable, right? Even in 1 dimension, you can reduce it. If the link function is arbitrary, you cannot do it. So basically, you need some global condition. And the global condition that we use here for the case of discrete valued multi-index models is that the surface area of the class of functions is bounded by some parameter. So surface area is basically a complexity measure of the partition, okay? And all the functions we care about really have decently bounded surface area. But this is something that's actually necessary. Otherwise, even information theoretically, you cannot. After you reduce to k dimensions, you cannot learn. Is there another question, Jerry?
For the SQ lower bound, you could hope to still get the 2 to the poly k, right?
Absolutely. So the correct dependence here is only as a function of d. The dependence on the rest is not necessarily optimal, okay?
Rule out that you could get that. Like the fact that you get polynomial time, like you still could show an SQ lower bound that's stronger than poly 1 over epsilon.
So I'm not sure I understand what you're asking.
Like you could hope for an SQ lower bound that's like 2 to the poly 1 over epsilon.
I mean, I don't know how to do that. In general, the methodology that we have that doesn't usually give you these types of guarantees. It gives you dimension to the something as opposed to 2 to the something. But yeah, it is possible. It is possible. All right, so now a few more applications and I'm done, okay? So another application is for intersections of half spaces. So it turns out that if you take an intersection of k half spaces, they're going to satisfy this definition of well-behaved, and the value of m, this m star, is going to be 2. Not 1 for multi-class linear classifiers, but 2. And then as a corollary of the general algorithm, we actually get the best known algorithm for intersection of half spaces with basically near optimal dependence on opt in the final error guarantee and fixed polynomial dependence on d. Okay? So there's a lot of prior work here. I didn't go into it. Some of it mine, some of it not mine. But basically, if you wanted like a near optimal error for this problem, the only thing that you could do is polynomial regression. And this is going to give you d to the poly 1 over epsilon. Okay? And this is what we're trying to avoid. And an adaptation of this general result that I stated in the previous slide can actually be worked out for real valued multi-index models, where now you're talking about learning under the L2 laws. This is a follow-up paper with a slightly different set of co-authors. We kicked out one student that is graduating, and we added another one. A corollary of that is that we can learn homogeneous ReLU networks with this complexity. So d squared, okay, times some function of k, which is the dimension of the hidden subspace, and L, which is the Lipschitz constant of the network. So there was a previous algorithm for this problem, a result by Chen, Mecca, and Clivans, which qualitatively similar to this one, but they also had an exponential dependence on the size of the network, like the number of gates. It was 2 to the number of gates as well, in addition to these parameters. So the improvement here is that we completely eliminate the number of gates from the complexity. All right, so if there are not more questions on this slide, I'll just wrap up. Yeah.
So what are the general conditions like under which sample complexity becomes like polynomial in D and K?
So the sample complexity, if you do not care about computation, is polynomial in D and K. Under computation, we know nothing. Okay. Yeah, so like we don't know. I mean, special results, sure, but even for a positive linear combination of values, we don't know how to do this. Okay, so for a single half space, for a single ReLU, we know how to do it. For a linear combination of values without assumptions, we don't know how to do it yet. Okay.
Let's say multi-class with like label noises totally like independent and everything like under some.
Yeah. No, we don't know how to do this. I'm happy to discuss offline. All right, so let me conclude, because I'm a little bit nervous about the time. So this talk was a sort of a survey of recent progress on efficient and robust learning of multi-index models. Of course, we want to do much more. Okay, we want to develop a general theory, and some of the results I presented could be viewed as a first step in this direction, but there's a long way to go. Now, in terms of concrete problems, there are many. Of course, if we want fully polynomial time algorithms, the question my friend asked, these techniques that I present are not good enough for that. And it turns out that even for a positive linear combination of values, we don't know how to quite do this. We have some progress with Daniel in a different work using different techniques that can give you polynomial in D and K. But there is also an extraneous 2 to the 1 over epsilon factor there that we don't know how to remove. For other activations that are a little bit more tame, like cosine, we can actually get a fully polynomial time algorithm, but none of this is actually practical. I would like to see an optimization-based method that works, and I believe it exists. We can look at settings where we have stronger access to the data, like the active model or query learning, and there are actually separations. We can do better in terms of complexity for multi-index models. And of course, this Gaussian assumption is quite restrictive and is used as a modeling assumption. We don't necessarily believe that data is going to be Gaussian. If you move to discrete distributions, like none of the things that we're using is actually true, and we need new ideas. But even for a single half space, we don't know how to do this properly. So I'm going to take questions if there are any.
Follow up on this question and ask you a question. So I think you're asking if it's an easy description or a simple description of algorithms for 2 classes. And I think there is a simple description, at least one of the first result in the direction was mine, you mentioned on the slide. And it's just like an adaptively chosen sequence of hinge loss minimization problems. So we prove it even under like Massar noise, very simple type of noise. If you just do one-shot optimization, like hinge loss minimization or other structure loss, that's not going to do well.
So it's an L1 penalty on the misclassified one.
Yeah, so like if you just do, we formally proved in a call paper, if you just do one-shot optimization of hinge loss or other nice structure losses, you're going to do terribly. But if you do instead of an adaptively chosen sequence of such loss minimization problems, that will going to work. And how the sequence is like basically based on localization. Now the question that I have for you, can you give us a simple description of your algorithm that you presented today? Like K equals 2, I describe it easily as being adaptively chosen sequence of hinge loss minimization problems.
Right.
So what is your algorithm if I ask you at the high level?
I mean, it's what I said, right? So basically you adaptively construct a partition of the space and you refine this partition until a constant function within each piece of the partition is good enough.
But this has a feeling of like nearest neighbor and feels like it's not the right sample complexity potentially.
It's absolutely not the right sample complexity, but it is the best thing that we know even for special cases.
No, I know, but it's like, yeah, I guess.
So the algorithm, because it works for a non-parametric family, it works for multi-index models where even the combining function is unknown. It cannot have sort of a simple hypothesis, at least as far as we know. Okay, if you focus only on linear combinations of values or on multi-class linear classifiers, there ought to be better algorithms. Indeed, we have some progress already, but it's not published. So it ought to be the case, but it doesn't follow from this framework.
Thinking about the special case of multi-class, classification.
Yeah.
Also, like the partition, this is like extremely specific to you're using the fact that like when you restricted it, it's like
Yes, it's absolutely it's absolutely using the Gaussianity. But let me also point out that we actually are able to get a factor which is a constant times opt, and like even for a single sort of linear separator, like binary classifier, linear threshold function, this is the most general class of distributions for which we can get a constant factor. So the results that Nina alluded to, her results that work for isotropic low concave distributions and give you a constant factor, they crucially, this is like a known but hidden secret in the community, they crucially use the fact that the half space goes through the origin. If you have a bias, it doesn't work and you need something else. And we were able to deal with this in a subsequent paper, but we only work it only works for the Gaussian. So if you can actually get constant factor under more general class of distribution, even for a single binary linear threshold function, it would be great progress.
Like you're not quite Gaussian, you're like watching sequence or something.
We haven't looked. I mean, this algorithm works also for the sort of nasty noise. So you can get a little bit of the Gaussian, also noise also in X. But other notions of distance like Wasserstein we didn't look at. I mean, it's even worse if you look at discrete distributions. Like just try to learn a half space over the hypercube in that model. We don't know how to do a constant times opt, even for homogeneous half spaces. So basically, since you're asking, like some of the properties that all of these algorithms are using, and they're not saying it explicitly, they're using concentration, which is not a problem. They're also using anti-concentration and anti-anti-concentration, that you don't have regions that are empty. So both of those things are crucial for all of these algorithms. If you don't have them, nothing works. So I would say that if you're interested, like for someone interested to get something for more general distributions, they need to first focus on the simplest models and try to make it work before you go to something so general.
Sorry, you're not just using anti-concentration. Aren't you also using like the algebraic structure at the moment?
For these results, not the algebraic structure, no. For these results, we're using the Gaussianity more, but for the specific sort of half space results, you don't need that.
Yeah, by the way, if you're not gonna get, I guess for your style of algorithm, this reminds me there is work on like Rashad and David and Gunnar and the probabilistic richness, also English time work. So they remind me very much of their algorithms. And there is work in the direction they go to more general distributions, something called probabilistic richness and so on. So you might want to check that out.
Thank you. If there are no more questions, I'd like to thank the organizers again for inviting me and everyone who stayed until like 5:17. And